Hello. Today we study exponential functions, differentiation and integration. Remember that we study the natural logarithmic functions, right? That is ln of x equal to integral from 1 to x dt over t for x greater than 0, right? And we know that this function has derivative ln of x equal to 1 over x, which is always greater than 0 because, x greater than 0. So our function is increasing, right? Increasing. You see? And since this function is increasing, and we know that such function, is 1 to 1 on each domain. And the graph of this function looks like this. This is 1. Okay, so look like this. Okay, the function is concave. We know that because if you take the second derivative, you have negative 1 over x squared, which is always negative. So the function is concave. And for such function, we can find inverse of it. Why? Because, for each x, you have one y only, right? I mean, for each x greater than 0, okay? We are talking about this domain. And for each y in here, there is only one x, right? Such that y equal to f of x. So that means this function has an inverse, okay? So from here I can write, ln of x has an inverse. And remember that we have the following, identities that have to classify an inverse function. F to negative 1x equal to x, and f to negative 1 fx equal to x. So I hope you remember this, right? So, that's how we can, determine, right, an inverse. So if you have two functions, you want to check if they are inverse of each other, just go ahead to check these two identities. Okay, so ln has an inverse. I will call such function as f to negative 1x equal to e to the x, and where e is such number that, ln of e, or the integral from 1 to e dt over t. This is ln of e, and this is 1, right? We studied the definition of e in the previous video, okay? This function is called the natural exponential function. Exponential function. And based on the definition, we have the following one. Y equal to e to the x if and only if x equal to ln of y, because they are inverse of each other. Okay, so this is the definition of the natural exponential function. All right, so from here we will have some very direct consequence. First one, ln of e to the x equal to the x. Second one, e to ln of x equal to x. You see? So, what is this? This is just, composite function, right? Look at these two properties. So if you rewrite that in this form, so you have two identities like this. ln you apply to e to the x, so ln and the natural exponential function will be cancelled out. You have x. And then if you apply exponential to ln of x, so that they will be cancelled out, right? You still have the x only. I'll tell you, this is very interesting, right? And very useful functions. Okay? Let's consider the following example. We have 7 equal to e to x plus 1. Let's solve for the x, okay? You see, in order to solve for the x, since you have exponential function in here, right? You may apply the first identity in here, okay? So you apply ln to both sides, you get ln of 7 equal to ln of e x plus 1. You see this? And then what's this? This is just x plus 1, right? Because of the first identity. And from here, you get x equal to ln of 7 minus 1. Okay? So, that's how we can solve, such functions, such equations involving exponential functions. Now, what happens if you have an equation involving logarithmic functions, like ln of 2x minus 3 equal to 5. So how to solve for the x? Again, right? If you have ln, you might apply the exponential function because you want to cancel that out. Is that correct? So I will apply e to both sides. I have e to ln of 2x minus 3 equal to 5. No, e to the 5. Okay, e to the 5th. And then, since on the left hand side, e and ln will be cancelled out, you have 2x minus 3 equal to e to the 5th. From here, you get 2x equal to e to the 5th plus 3, and then you divide both sides by 2, you get e to the 5th plus 3 over 2. Of course, you can use calculator to find this number, right? It's pretty easy. It's approximately equal to 75.707. All right. Now let's move to some properties involving exponential functions. So the first property looks like this. You have e to the a times e to the b equal to e to a plus b. The second one is e to the a divided by e to the b equal to e to the a minus b. If you look at these properties, you would think about, properties of the natural logarithmic functions. Let me write it down, and then we will have some comparison, okay? For logarithmic function, log of a product with the b equal to log a plus log b. And log of a divided by b is log a minus log b. So you can see exponential function, right? If you apply exponential function to a sum, right, you get product. You see this? If you apply exponential function to difference, you get a quotient. And a logarithmic function works in the opposite way, right? Logarithmic function, when you apply a ln to the product, you get a sum. And when you apply ln to a quotient, you get a difference. You see that? Because they are inverse of each other. Does that make sense? So, sometimes if you want something, it really depends on the situation. You might need to choose, right, which function you use. Okay? But I tell you, they are really, really important. Okay? All right. So we already know the function y equal to e to the x, right? We know this happens if and only if x equal to ln of y, because they are inverse of each other. And this function is the inverse of ln of x. So from the previous video, we know the graph of inverse functions are symmetric with respect to the y-axis. No, not the y-axis, with respect to the y equal to x, right? So you have x, y in here. This is the y equal to x. Okay. Suppose you have 1 right here. I can write 1 right here. So, that's symmetric. Another one look like this. This is one function. Okay. This is the one function. I think this is ln of x. So if they are symmetric, so you would think about, yeah, you have the following one. Okay, and this is the equation of the graph of e to the x. Okay, they are symmetric with respect to this a6. So here's a very good thing we need to memorize. The graph of ln of x pass through the point 1, 0, while the graph of exponential function e to the x pass through the point 0, 1. Don't forget that. Okay, when we study a general exponential function or general logarithmic functions, those graphs also pass through these two guys. Okay, logarithmic functions, yes, the graph pass through this point. Exponential functions has graph passing through this point. That's it. All right. So from this picture, we have some informations like this. The first one, the function y equal to e to the x is increasing, right? The second one, this function is defined everywhere. The domain of this function is the whole number line. Is that correct? And the range in this case is R plus. I'll tell you, right? This property is very important, very interesting. You might think about sometimes you need to work with non-negative numbers, right? Okay, any x, whatever, you get x, right? But when you apply exponential e to the x, you get a positive number. Okay, so that means exponential function convert any number into positive. Don't forget that. That is very useful property. Another thing is, since the function ln of x is increasing, our function is also increasing, as we have seen, and ln of x is concave, right? So that means e to the x is convex. Okay, e to the x is convex. And from here you can see the limit of e to the x when x approaches infinity is equal to infinity, right? And the limit of e to the x when x goes to 0 is equal to 1. Okay, is equal to 1. Oh no, I think that is obvious, because the graph passed through this point, so this is obvious. So let me erase this. Let's consider the limit of this function at negative infinity, so that is 0. What does it mean? That means y equal to 0. This property says y equal to 0 is an asymptote. Okay, in horizontal asymptote. Okay, let's write that. Let's talk about derivatives of exponential functions. It's pretty easy because we know how to take derivative of the inverse function already, right? So we know that ln of e to the x equal to x. If you differentiate both sides, you get ln of e to the x equal to 1, because the derivative of x is just 1, right? And for this part, you use the chain rule. You have the following one: e to the x derivative over e to the x equal to 1. So that means the derivative of e to the x is just e to the x. You see, it's very, very good property, right? You differentiate that function, you get the same one. And from here, of course, if you have e to the u, where u is a function, you have e to the u and u prime. That is the chain rule for exponential function. All right, example. Let's find derivative of e to 4x squared plus 1. So you get e to 4x squared plus 1, that is e to the u, right? And then u prime 4x squared plus 1 derivative. That is e to 4x squared plus 1 times 8x. All right? It's pretty easy, right? But, it's very good. I'll tell you this, right? Each time when you differentiate e to the u, you still have e to the u. That is very, very nice property. Because, at first, when you look at such function, right? And sometimes, they ask you to find extrema of exponential functions. You say, oh, it's difficult. No, but actually, when you differentiate that, this part is always positive. So you don't need to put that equal to 0. You only need to solve, this part equal to 0. That's it. So it is not that bad at all, right? When you see a such function. Okay. Let's consider another one. You have y equal to e to 3x over e to x plus 1. Okay. So if you need to find the derivative of this function, no problem. In this case, we have quotient. We need to use quotient rule. So I have y prime equal to e to 3x derivative times ex plus 1 minus e to 3x times ex plus 1 derivative divided by e to the x plus 1 square, right? And for the first term, I use the chain rule. I have e to the u times u prime, which is 3, okay, ex plus 1, minus e 3x, and here one derivative is 0, e to the x derivative is itself. So I have e to the x plus 1 square, right? And if you want to set this equal to 0 and solve for the critical points, right, it's also nice. Look at this. It's just extra, right? If you put f derivative equal to 0, so you put the top equal to 0, right? You have e to 3x. Okay, I write 3 in here. Ex plus 1 minus e to 3x ex, right? Equal to 0. And you see, you have this term, this common, but that is always bigger than 0, so I can cancel that out, right? So I still have 3 ex plus 1 minus ex equal to 0. You see this? And we have 3ex plus 3 minus ex equal to 0. And that is 2 e to the x plus 3 equal to 0. So from very, very big equation, you got this one. And from here, of course, in this situation, we have no solution because e to the x is always positive and 3 is always positive. So the left-hand side part is always positive. So we don't have any solution. This example just show you, right? Sometimes if you need to work with exponential functions, just go ahead to do that. Don't be afraid of them, okay? They are not really bad, okay? All right, so let's consider the following example. Find the relative extrema. So that's what we did, right? A lot in calculus 1. And our function now involves exponential function x e to the x. Let's find the derivative, right? That is the first step. So f prime, or let's say y prime, it's okay. Equal to, we need to use the product rule. So x derivative is 1 times e to the x plus x. E to the x derivative is itself, so I have this, you see? And then I will factor e to the x out. I have 1 plus x, you see? It looks very nice, right? And then you solve y prime equal to 0. So I have e to the x 1 plus x equal to 0. But e to the x is always positive, right? This equation is equivalent to 1 plus x equal to 0. And you have x equal to negative 1. The function has only one critical point. You can classify that easily. You make a chart, x, y prime, and y. The function is defined everywhere from negative infinity to positive infinity. You have negative 1 in here. At negative 1, the derivative is 0. Now you need to consider the sign of the derivative. When x bigger than negative 1, this guy is positive, right? So the derivative is positive. Here is negative. So the function is increasing in here and decreasing in this interval. And the function attains relative minimum. And not only, it's global minimum at negative 1. So you plug negative 1 into the function. Here's your function xe to the x. You will get negative e to negative 1. So this is your minimum. Okay? In the following example, we'll see a very important application of exponential function. So in probability theory, we have the following normal density function. We call the bell-shaped curve, right? And this function fx equal to 1 over square root of 2 pi e to x squared over 2 is the standard normal probability density function, and the graph of such function look like this. Look like a head, right? A bell. Sometimes this is called the bell-shaped curve. Okay, and they ask us to show that this function has two inflection points when x equal to negative 1 right here and 1. Okay, and if you pay attention, actually, everything in negative 1 and 1, right, looks like, with a higher probability, right? So let's check that. Okay, so let's copy the function in here. In order to check points of inflection, we need to find the second derivative of such function. So I have to take the first derivative, f derivative of x. So this is 1 over square root of 2 pi in here. And then I need to use the chain rule. In this case, u is equal to negative x squared over 2. Okay, so e to x squared over 2 times u prime. I have negative x only because, what is u prime? That is just negative x, right? That is the first derivative. And then let me rewrite this as negative 1 over square root of 2 pi x e to x squared over 2. Let's find the second derivative. Of course, you don't care about this, right? Because that is just coefficient. So I take the second derivative. I have negative 1 over square root of 2 pi. And then I use the product rule. I have x derivative is 1. So I have e to x squared over 2 plus x, right? Again, we take the derivative of this guy. That is e to x squared over 2 times negative x. We already have this right here. Okay. All right. Now I will factor e to negative x squared over 2 out. I have negative e to negative x squared over 2 divided by square root of 2 pi. Inside I have 1 minus x squared because you have x and negative x. That would be negative x squared. You see? And you set this equal to 0. This is equivalent to that 1 minus x squared equal to 0. And you have x equal to x squared equal to 1 or x equal to plus minus 1. You see? So we have two inflection points, right? And of course, if you want to see, we can make the chart for the second derivative. All right, let's make the chart for the second derivative, right? We see where the function is convex, where the function is concave, x, y, 2 prime, and y in here. The function is defined everywhere. So I have negative 1, 1, and positive infinity. At negative 1 and 1, the second derivative is 0. Okay, now we have 3 intervals. We need to pick at least one point from each interval and plug into the second derivative. Plug those points into this expression to see if the second derivative is positive or negative. But we have negative in here, right? And this part is always positive. So, it depends on the sign of 1 minus x squared only, right? So I will pick 0 from here. I plug 0 into this. I got 1. 1 positive with the negative would be negative. And from here I can pick 2, right? I plug 2. I get 1 minus 2 squared is negative, but we have negative in here, so that means we have positive in here. Similarly, we have positive in here. That means the function is convex in this, and then concave, and then convex. You see? So it seems like, yeah, you have something like this: convex, inflection point, concave, inflection point, and then convex. That's what you have seen in the picture in here. Okay? Now let's talk about integration of exponential functions. So, from the previous section, the derivative of e to the x is e to the x. So that's why antiderivative of e to the x, that is e to the x plus c. It's pretty easy, right? And pretty nice. You see, it's very nice. And of course, you have e to the u. The u is equal to e to the u plus c, if u is a function of x. Okay, so exponential functions this function is pretty nice. The derivative is the same, right? And antiderivative is also the same. Okay, let's consider the following example. Find antiderivative of e to 3x plus 1 dx. So in this case, u is 3x plus 1. If you are careful, you can do substitution. Yes, you put u equal to 3x plus 1, you have du equal to 3 dx, right? Or dx is equal to du over 3. Remember that when we do substitution, we need to rewrite the original integral in terms of new variable. So this integral is equal to e to the u, dx is du over 3. So that's why I have 1/3 eu du, and we know this is just 1/3 eu plus c. And at this step, you need to plug the substitution back here. You get 1/3 e to 3x plus 1 plus c. Is it? All right, let's move to the next example with this one. X e negative x squared dx. So if you look at such integral, you might think about e to the u, right? So you need to put u equal to negative x squared. And from here you get du equal to negative 2x dx. And you look at the original integral, you have x and dx. You see, this combination I mentioned several times when we study integration, right, for logarithmic functions. So from here I get x dx equal to negative du over 2. And now we are ready to rewrite the original integral in terms of u. Let's denote by I. So integral I equal to e to the u and negative du over 2. That is negative 1/2 e to the u du, and that is 1 over 2 e to the u plus c, right? And now you plug the substitution back here, you get 1 over 2 negative e negative x squared plus c. So it's not that bad, right? But from this example, we can say if they give you the following integral, there's no way to solve that. Integral of e2 to the x squared dx. There's no way, right? We don't know. At this moment, we don't know how to solve such integral. But in the future, yes. Okay? Because in this case, yeah, if you put u equal to negative x squared and you differentiate that, you get negative 2x dx. You don't have x dx in the integral. So, sometimes it's not that easy, right? But it depends on the situation. We know we will learn how to solve such integral in the future. Okay, so now let's move to more examples. That is the only way to learn mathematics. We need to do more examples, right? Say antiderivative of psi of x e to cos of x dx. So you may guess we need to put u equal to cos of x, right? And from here I get du equal to negative psi x dx. So we see psi x dx, psi x dx. That is good. I have psi x dx equal to negative du, right? Now we can rewrite our integral as integral of e to the u and negative du. I try to keep that order, and that is negative eu du. So we know this is negative eu plus c, and we plug the substitution back here. We get negative e to cos x plus c. So if you pay attention, actually we just do integration with substitution. The only thing different is we involve exponential function, right? Like previous topic when we studied the natural logarithmic functions. So basically we do substitution but with new functions. That's it. Okay. So I hope that this topic is not that difficult. Let's do a couple more definite integrals and then we finish today's lecture. Let's find the following definite integrals. Ex over 1 plus e to the x dx. Integral from 0 to 1. All right, so again, right, we need to do substitution. But how to do substitution in this situation? You have different ways to do that. Okay, but on the top, you see the following combination. E to the x dx. And we know that e to the x is very special function. When you differentiate that, you get exactly e to the x. So what do you think about that? You have 1 plus e to the x in the denominator. So you may think you put u equal to 1 plus e to the x, right? And in this case, you have du equal to e to the x dx. You see, you have e to the x dx on the top already, you see. So it seems like this is a good substitution. Okay, let's move forward with this. So I put u equal to 1 plus e to the x. I have du equal to this. Now I will rewrite my integral. Okay, so at this moment I don't want to write integration limits. I just try to find antiderivative. Okay, so antiderivative e to the x dx 1 plus e to the x equal to on the top I have du. In here I have u, right? And we know that is what? That is ln of absolute of u plus c, right? And that is ln of 1 plus e to the x plus c. At this step, I will plug 0 and 1 into this function. So my definite integral ex dx over 1 plus ex equal to ln of 1 plus e to the 1 minus ln of 1 plus e to 0. So basically, you have ln of 1 plus e minus ln of 2. You see? And if you use the calculator, you may find that that is just approximately equal to 0.6 and 2. All right? This is just one way, to do substitution. You may do a very naive substitution, like you put u equal to e to the x. I would challenge you to solve that. Okay? To the end. Let's do one more with trig functions and exponential altogether. Okay? We need to evaluate the following integral from -1 to 0, e to the x cosine of e to the x dx. All right, so from here, probably you might guess you put u equal to e to the x, right? Because there's no way to evaluate integral of cosine of e to the x. So we need to change this. We need to put this equal to u, right? E to the x. And when you differentiate, you get ex dx. So, which is good, ex dx, right here. And again, right, we need to find antiderivative. So I write ex cosine of ex dx equal to cosine of u du, and that is sine of u, right, plus c, and that is sine of e to the x plus c. And from now I can plug -1 and 0 into this function, e to 0 minus sine of e to -1. Okay, so that is sine of 1 minus sine of 1 over e. And of course, if you want, you can use calculator and you can find the number right here. So this is just some examples, right? Very typical examples involving exponential functions. So in the future, when we study more difficult integrals, so we will learn like integration by parts, everything else. But we'll go back to such function. Okay, so I hope that you enjoyed the video. If you have any questions, feel free to let me know. Thank you.